Take a block of ice. Leave it out, it collapses into a puddle. Add heat, it quickly boils off and vanishes into the air. We see these transitions every day, but the physical mechanics are entirely hidden from us. What is actually happening to the invisible building blocks of these materials as they transform? A solid object, like a piece of chalk, looks like one continuous, unbroken mass. But when you grind that chalk into a fine powder, you aren't changing the substance itself. You are simply revealing that it's made of individual pieces. If you could zoom in infinitely on that dust, you wouldn't find a smaller solid mass. You would find incredibly tiny, individual particles separated by a vacuum of completely empty space. Think of solid rocks, flowing liquid water, and the air we breathe. They all share this same particulate nature. Their drastically different behaviors in our world are driven by how those particles interact in the gaps between them. Inside all matter, two factors are locked in constant conflict: interparticle forces pulling particles together, and kinetic energy pushing them apart. In a solid, attractive forces overpower kinetic energy, locking particles into a tightly packed formation. These particles are never actually still. They have enough energy to continuously vibrate in place, but they lack the strength to break their bonds. Even in this dense state, they aren't touching perfectly. Microscopic voids exist even between the most tightly packed particles. Because the attraction is so much stronger than the motion, the substance holds its shape. That dominance of interparticle force is why a solid remains rigid and unyielding. Adding heat directly increases the kinetic energy of these particles, tipping the tug-of-war against the attractive forces. The melting point is the exact temperature where that motion finally becomes strong enough to overcome the strongest solid bonds. At this stage, the particles can finally slide and roll past one another. This movement is what allows liquids to flow and conform to the shape of any container. This explains why sugar seems to disappear when you stir it into a glass of water. It hasn't vanished from existence, it's just breaking down into its smallest building blocks. Those sugar particles slip perfectly into the empty interparticle spaces that already exist between the sliding water molecules. The liquid state is a temporary compromise between attraction and motion, providing the flexibility required for substances to mix and flow. Extreme heat, like 100 degrees Celsius for water, gives the particles so much kinetic energy that it completely shatters the remaining interparticle forces. A gas is an environment of random, high-speed motion, where massive empty spaces exist between isolated flying particles. Because of those vast empty spaces, gases can be easily squeezed into smaller volumes inside syringes. You can't compress a liquid this way, because the particles are already sitting close together. We can prove that heat dictates this particle speed by watching diffusion, the way substances mix on their own. If you drop a crystal of potassium permanganate into water, the purple color begins to spread. In cold water, the color moves slowly. In hot water, the mixing is rapid and violent. Higher temperatures give particles more energy, forcing them to mix faster. Completely overpowering the attractive forces frees a substance from all structural constraints, allowing it to rapidly expand and fill any available space. We use these massive interparticle spaces to our advantage, packing life-sustaining air into high-pressure compressed gas tanks for deep-sea exploration. Mastering these extreme phase changes and the controlled expansion of gases provides the massive propulsion required to launch rockets into space. On a planetary scale, these same microscopic shifts in temperature, spacing, and pressure are what drive our weather patterns and storm systems. Every puddle that boils away on a hot sidewalk is a record of kinetic energy finally snapping the last of those interparticle attractions. If phase changes only push the same particles further apart, imagine the explosive possibilities when we actually break the particles themselves to build entirely new substances.